Hi everyone, and today we're going to solve a digits LeetCode easy problem, and we are going to use solve it using two different ways, iteratively and mathematically. So at the beginning, let's dive into the definition of the problem. We have a number. Repeatedly add all its digits until the result has only one digit and return it. The number is 38. You can see that we need to return 2. Why? The process is explained here. We have 38. We just summarize all its digits, 3 plus 8, till we get only one digit. But we haven't got one single digit here. We got a number because the digit is a value from a 0 to 9, but we have a value higher than 9, so it's not considered a digit. It's considered a number. So we have to decompose this number further. 11 is 1 plus 1. We summarize all its digits till we get one single digit, which is in our case is 2. For someone who is familiar with math concept, which is called decision root, it's going to be a little bit more easier. But who doesn't know, please pay attention to this one. I will explain it. It's very interesting and required for us concept because we need to understand the properties of digital root firstly to derive a mathematical solution. Okay, so what is digital root? Digital root is important math concept providing characteristic value that helps describe the divisibility properties of the number as well as providing some remainder relation properties. Okay. For iterative solution, we don't need to worry about these properties. We just summarize it. We're summarizing digit by digit till we get one single digit. Okay, let's define our digital root variable. It's going to be 0. This is our sum of our digits. We are starting from here, for example. We have to find the way of how to extract number by number from our, digit by digit from our initial number. How to do it? When working with numbers, there is a simple workaround of doing it. It's called it's not called, it's just explained like this. We are dividing by 10, and it helps us to chop our last digit, and taking the remainder when dividing by 10 is going to provide us last digit. So we need two operations, floor division, and the second one is modular operation. In Python, we have a single one function for it. It can be implemented. It can be implemented during two lines of code. But in Python, it's more convenient. You can use just floor division and modular operation in one function. So we are providing here our number, divide by 10, and the result of this function is our two variable tuple, which we can put into our two variables, is our number, which is already the number divided by 10s, and last digit as a reminder. And what we have to do, firstly we have to check whether our number is more than 0, because we need to when we are chopping till this moment, we have to understand that our we walk through all the digits. So we need this loop firstly. In this loop, we are calling diffmod operation to extract our new number and last digit. We need our last digit to be added into our digital root. Sorry, last digit. And right now we are sitting here, and we need to check whether this is a final digit, one single final digit or not. How to do it? Firstly, we have to understand that our number has to be 0. We have to come till the end. So at the end, our number is going to be 0. And if our digital root by itself is higher than 9, if it's higher than 9, then it's not considered a digit, it's considered a number, and we have to decompose it further to calculate our sums. And what we should do in this moment, okay, we checked, we're in here, and we have to, as you can see, reinitialize our number and digital root. From here we started as this was our number, this is our digital root. We have to reinitialize our number to be digital root, and our digital root is going to be 0. And this operation iteratively is, how to say, starts from the scratch. So okay, reinitialize now number with digital root, and our digital root is going to be 0. That's it, and we are done. If we come till the end and its digital root is less than 10, then it's really digital root which we have to return, and let's return it, digital root. I want to stress that if we came to this moment, our number is going to be 0 here because we are done. It's no 11 already in here, it's 0, and our digital root has to be somewhere from 0 to 9. And I even created some test cases. We can think something new and run our code. It's invalid because, of course, I forgot our if statement, if number equals 0. Let's rerun it. Again, doesn't work. Name n is not defined. Where is our name n? Yes, we don't have n, we have number. Let's start one more time. Yes, and everything works fine. What is the time complexity of this algorithm? What is the time complexity? Let me just copy the information from my notes. Let me copy it. I'll copy it here, and even let's take it here. That's it. Okay, time complexity is going to be a little bit difficult and complicated for this for finding digital root. In some sources it's called to be O log n. In some sources it's explained as O(n) plus O log n plus O log n. But I came to the fact that both time complexities are right, and I want to explain that how it works, why we have two time complexities, and let's just look at the examples. We have a number of, for example, we have three numbers. All three numbers is our 9 digits numbers, In first case, we summarize it into 59, all our 9 digits, then into 14, and we came to the final 5 when we add 1 plus 4. In total, we have had 13 digits to iterate. When we take this huge number and as you can see, applied from these numbers summarized to 2 digits number, you can see that our initial number drops hugely, massively drops, and our time complexity is going to be approximated to be logarithmic, or log n. If we will take logarithm from this number, you can see that we don't have 59, we have approximately 8.45. The question is why? The answer is simple. It's a rough logarithmic approximation for the sum of the digits. Its logarithm doesn't provide the exact number of digits to iterate, and it depends hugely whether our number is divided by 9 or not. By 9 or not. Here's our second and third solutions. You can see that in second we have had 11 digits because I decreased a little bit our sum so our second second digital root which we have derived from the first walkthrough was divided by 9. 5 plus 4, 9. In this case, 5 plus 9, 14. And we have to decompose it further. In the third case, all of the 9 ones exist. So if we will summarize them, we just simply get 9. So we have to only iterate over all our 9 digits. So you can see that in first case it's 13. In the second, it's 11 digits in total to iterate. In the third, it's 9 digits in total to iterate. And it's much closer to our logarithm. So this rule works like this. But why log n? Because in here we hugely drops from our initial number hugely drops to small number in logarithmic time complexity by logarithmic formula. In this time complexity we have had 13 digits to iterate, and it was approximately SON. Firstly we have had 9 digits, then we have had 2 digits, and then 2 digits, and that's it. So ON plus O log n plus O log n, and so on and so on and so on. Again, this is a rough approximation. It's not real number. When applying logarithm, it doesn't provide you the real number of digits to iterate. It's explained also on Wikipedia. For any fixed base, the sum of the digits is going to be O log n, is going to be of a number is proportional to its logarithm. But n digits, number digits to iterate is going to be O log n, O log n. Okay, that's it. Let's remove this right now. And we are interested in our mathematical. Okay, we've done with our iterative solution. Right now, let's dive into mathematical solution. We need to, again, digital root and digital root properties. One more time, it helps us to define whether our number is divisible by 3, 6, and 9. Let me provide you the divisible properties from here. Okay. you can see, for example, about what properties I'm talking about. Let's just imagine we have an even number, and if we just have an even number, it's 100% sure that it's divisible by 2. If we have a value that ends on 5 or 0, it's divisible by 5. If it ends on 0, it's divisible by 10. So there is a logic which we derived from the math basic classes. But what about digital root? If we have digital root which is 3, 6, or 9, it's divisible by 3. If its digital root is 3, 6, or 9 plus it's even, it's divisible by 6. And if digital root is 9, it's divisible by 9. We can simply check it. For example, if we take 39, because here 38 provides us 2 as a digital root. We need 39 to have 3. We understand that 39 provides us 3 in digital root. So if it's 3, it has to be divisible by 3. Let's check it out. 39 divisible by 3 without remainder. Yes, it's 13. So it's completely divisible by 3 without the remainder. Okay, what about 6? It's not an even number. So it's not divisible by 6. Let's check it out. 6.5. The remainder exists. So it's true. Digital root is 9. It's divisible by 9. We have digital root 3. So if we will take 39 and divide it by 9, it's not going to be divisible without remainder. So this is how this divisible property works. This is why digital root is important to know. And what about the remainder relation properties? This one helps us to derive mathematical solution for us. Let's one more time create this. I copied this again from my notes. Here it is. The remainder relation properties. Okay, let's look at different initial numbers from 10 to 19, and let's calculate our digital root for each of them. For 10 is going to be 1. 1 plus 0 is going to be 1. 11, 2. 1 plus 1. 13, 14, 16, 17, 17, 8. So you can see 17, 8, which is 8 more than 9. 10 is 1, and 1 more than 9, and so on and so on. We look at this a moment. We have 18. Digital root is 9, which is 9 more than 9. Let's look at the remainder when we are dividing by 9. I'll explain afterwards why we are dividing by 9. If we will take the 10 and we will take the modular operation and divide by 9 and take the remainder, it's going to be 1. For the second, and this one relates 1 by 1 to this digital root. It's similar. In the second case, 11, it gives us 2 digital root, and remainder is 2. 6, 6, 8, 8. But when we are talking about 9, it's 0. So remainder of 0 provides us digital root has to be provided 9 and not 0. So we see that the logic that we don't need to calculate, iterate over all of these digits to summarize, and afterwards to provide our one single digit, which is our digital root. So we don't need to do it iteratively. We can do it mathematically, and just by dividing by 9. Why by 9? Because dividing by 9, you are just mapping your initial, your initial number into values from 0 to 8. This is how it works. We can, for example, check Let's check it. Let's divide it by 2. Let's take a modular operation of 2, divide it by 2 and take the remainder. I want to provide you, let's take, for example, this input number, random input number. Let's take an modular operation of 2. It's going to be 1. If I will a little bit increase it, it's going to be 0. So it doesn't matter how I change my number. Anyway, I'm going to be given values from 0 to 1. In our case, we're going to be given values from 0 to 8. So it's what we need. We need to map our values from 0 to 9. But with 9, we have some corner case. It's a little bit complicated. We having the 0 reminder, we have to return 9. And not just 9 by 9, because if we will take our initial value and divide it by 9, it's going to be 0. For example, 18 divided by 9 is going to be 0. 9 divided by 9 is going to be 0. And when we have in this 0, we have to return 9. This is just a simple property of taking the reminder. And what the moment to mention is, okay, for the 0 we have to return 9, but what we have to return for the 0, if really 0 is 0. If 0 is 0, we have to return 0. This is simple, because if in logical, if we have a value 0, for example number 0, we have to return 0. 0 plus we have only one digit 0, and if we will even summarize our 0 with 0, we get 0. It's just all about 0. So let's write this mathematical solution extracted from these reminder relation properties. If we have number equals 0, what we should do, we should return 0. This is this case. Okay, we reinitialize the logic for 0. If our real number taking the modular operation equals 0, that's it. 18 divided by 9 equals 0, and 9 divided by 9 without the reminder equals 0. What we should do, our reminder is 0, we should return 9 in this case. And what is remained is, if we just remove it, for example, we remove this, all other strings, all other rows provides us that it's identical one by one. If we have decision root, or it's not decision, digital root is equals 5, the reminder equals 5. So let's return num modular operation 9, and that's it. This is simple mathematical solution which works. We can even submit it. It works, it's fast, it works, and it doesn't care about how big our initial number. It doesn't matter at all, it doesn't count, we doesn't have to iterate digit by digit. So this is why this is the most efficient solution which can be provided using and calculating digital root. So what I want to say at the end, that thank you. Thank you for listening, thank you for watching, and have a happy coding day. Bye bye.